We're now going to look at problems that involve uniform electric fields. And as it says here, a uniform electric field refers to an electric field that is constant in both magnitude, so the value, for example, 10 newtons per coulomb, and the direction of the electric field. For example, let's shoot down here, downward. So we'll get to the details of what's down here in a moment, but if we have an electric field downward, so it's an arrow pointing down, if it is uniform, then what you will visually see on the paper in front of you is equally spaced straight lines. That tells you that you are dealing with a uniform, constant field value, constant direction. So I'm going to introduce a few of these characteristics, like the equal distance between adjacent line means a uniform field, and the line spacing will give us a direct indication of the field strength. In this lesson, and I'm going to reinforce it and give a more formal explanation in our next lesson as to how to draw these field lines and more about the features of the field lines. As far as the field spacing goes, and saying that it's directly proportional to field strength, it is exactly what that terminology says mathematically. So over here on the right-hand side, if I have an electric field down and it's uniform, so equally spaced lines, if, for example, the spacing over here was 1 centimeter, and if, for example, that 1 centimeter field represented a 10 Newton per coulomb field downward, if you were told the spacing over here is a half of a centimeter, then you would know the electric field strength over here is 20 newtons per coulomb. So we'll be doing more with this in the course as we go along, but again, wanted to introduce this up front to get us thinking kind of in the right direction right from the start. Now, the homework problems we're going to be dealing with in this for this lesson will not really involve the field maps. That'll be more in our next lesson, but for right now we're going to be really utilizing this equation, F equals QE equals MA. So that will be our go-to equation for our numeric problem solving for this page of notes. So if we rearrange that as it shows here, so please get this into your notes, A equals Q divided by M on E. So the acceleration value that a charge, little q, shown here, feels in the electric field. So that little q is the charge that's in the electric field, and m is the mass of the charge in the electric field, will affect the acceleration value, right? So the larger the q value, the greater the acceleration. So a q of 10 coulombs will have twice as much acceleration as a q of 5 coulombs. And of course, a lighter particle, a smaller mass, has a larger acceleration, and if the field that it's in itself has a larger value, then of course you have a larger acceleration. Now, the other thing we definitely need to know for this page of notes and for these homework questions is, what does the positive or negative q tell us about the acceleration? Well, if the q is positive, so let's use green for positive. If the q is positive, then the acceleration will be in the direction of the electric field. If the q is negative, then the acceleration points against the direction of the electric field. Okay? So that is important because we need to know which direction is the force. Is it an upward force or is it a downward force? And the acceleration, of course, goes with the force direction. So basically the homework questions boil down to constant acceleration problems, and as it shows here, we use our A equals Q on M times E to get the acceleration, and once the acceleration is known, then it really goes back to mechanics type problems from last year, so we'll see more of that. Well, the last thing I have here is just a conceptual question to, I hope, give you a better feel for how the particles, a more visual feel for how the particles are pushed or pulled in these electric fields. So here it says, what can we say about the 4 particles shown in the figure above? Above is actually below, so let's cross that out and just that's below. Assuming all 4 were injected into the uniform electric field horizontally along the dashed lines shown, and as it says here, for this discussion we are going to assume that all 4 have the same initial velocity horizontally. Well, what can we say? Well, if we look at particle 1 and particle 4, we know that both must be negative. Both must be negative because they were pulled upward against the direction of the electric field downward. And since the purple one was accelerated more strongly, it hit around the middle of the plate as opposed to the light blue one, particle 4, hitting at the end of the plate, we know that acceleration 1 has to be greater than acceleration 4. So if they had the same initial velocity, that means only one thing. Well, the electric field, of course, was the same for both. So that means that the charge to mass ratio of particle 1 must be greater than the charge to mass ratio of particle 4. A particle that goes through undeflected, whether it's a weak field or a strong field, it means only one thing: no net charge. So 2 is neutral. The final thing we have here is that the pink particle was pulled in the direction of the electric field, so I know that it must have been positively charged. And since, by symmetry, since we have an identical situation as to the purple particle 1, we can make a symmetry argument here that by symmetry, we know that the charge to mass ratios must have had the same magnitude. So Q3 was positive, right? The Q1, of course, was negative, but their charge to mass ratios must have been the same if you had perfect symmetry on the top and the bottom. Well, hopefully this gives us a better understanding of how to handle the charged particles in uniform electric fields. We'll use our F equals Q equals ma and our constant accelerations to help you problem solve, and I think we are going in the right direction.